right, let's get started. Okay, so we will carry on with our new topic on graph algorithms. So last time it is our first lecture on the search algorithms on the graph, which is called breadth first, right? So basically, as the name indicates, the breadth first search algorithm on the graph, it will spread across the graph from one source as broad as possible. Okay, so the results is a of a breadth first tree is a breadth first of a BFS is a breadth first tree, and the node in each node in the tree in the BFS tree is actually corresponds to the same vertical in the graph, and the number, more importantly, the number in the resulting BFS node is actually the shortest path from the source node, from the source vertex to that current vertex. And in the case of BFS, the way we define the path is by counting the number of edges. Okay, so far we didn't we haven't considered any weighted edges yet. Okay, so at least for the BFS and DFS, for the search algorithms covered in this course, we are not considering the weights on the graph, but that doesn't mean the weights is not important. The weights will be considered in the more advanced graph algorithms that we will cover in 2 lectures later. All right, so let's look at another concept that we quickly covered last time, which is the shortest path. Okay, so a shortest path is actually found by running a DFS on the basically any source vertex, and in the graph given a source S, the shortest path returned is indicated by this delta, and we will come across this delta again in the future lectures. So it is called, it is defined by the minimum number of edges in any path from S to V. So basically, this quantity delta is unique. So given any 2 vertices on the graph, we can always find the shortest path between 2 vertices, but that doesn't mean the path is unique. Okay, it doesn't mean the path is unique. We can sometimes there are multiple passes between 2 vertices that are of the same length, right? That are of the same distance. Okay, so this delta is unique, but the shortest path can be there can be multiple shortest paths. So the shortest path is not the unique one. It can be multiple shortest passes. Okay, but we say that as long as a path that has the shortest path distance, then we say this is a shortest path. All right, so last time I said that you can refer to the textbook to see how the correctness of BFS is proved, and also we have the function for printing the shortest path given the source and given the target's vertices on the graph. So I will publish a quiz question on this later after the lecture today. Okay. All right. So today the topic is DFS. So compared to BFS, the names already indicates the difference, right? So the breadth first search will go as broad as possible, but the depth first search means we prioritize the depth. That means when we explore the graph, we will go as deep as possible. And when we reach the point that we can go no deeper, then we will trace back. and we'll trace back to the previous vertex to choose another branch, to choose another way to go as deep as possible. So that is the basically the difference. And as organized in the slides here, we will, after we have covered DFS, we'll see that there are two applications that uses DFS as the basic operations. So, and that also relies on a very a kind of advanced version of DFS implementation. So we can implement DFS in basic two ways: recursive way, a recursive DFS, and the iterative DFS. And we will first cover these two implementations, but both of these implementations are kind of simple, a simple implementation. And in order to apply DFS to the future applications, then we need a more advanced and more sophisticated version of DFS. And we will cover that sophisticated version as the third algorithm today. So let's get started. Okay. All right. So the strategy, as the name indicates, is to go deeper in the graph whenever possible. Okay. So by deeper, I mean if there is any adjacent vertices, then the algorithm will choose to go dive deep into that adjacent vertex. Okay. So it basically explores the edges out of the most recently discovered vertex that still has unexplored edges that leaving it. Okay. And once the vertex V has been explored, then it will search back. It will go backwards to explore the edges, leaving the vertex from which V was discovered. Okay, so that may be a very, give me a second. Okay, I need to leave for a second. My daughter is knocking the door. All right, let me resume recording. Okay. So, but we'll see the strategy is more in a more concrete way by looking at some examples. Okay, so I'll show a very simple graph here, which has 5 vertices and 7 edges. It's a directional graph. Okay, so think of DFS because we want to go as deep as possible whenever possible. For example, if we start from the vertex 1 as our source, then we can randomly select to go to vertex 2 as our first step. Okay, then after 2 is discovered, we will not go back to 1, but we will go deep. That means we will go, iterate, we will like choose one, pick one vertex among the vertex 2's adjacent vertices. For example, we pick 4 and we will go to 4. Okay, and after 4 is discovered, we do not go back to 2 again, but we will start from 4 and go one more step deeper. And for example, if we reach 5, and after 5 is discovered, because 5 has no more output edges, so there's no way to go one more step deeper. So we'll go back to 4, right? And 4 also have no more edges out, right? We'll go back to 2, and 2 actually have one more edge, but that edge leads to 5, which is already discovered. So there's no need to go through this step again. So we will go back to 1 and to see if there are any other possible ways out from 1. And we will find the last undiscovered edge here from 1 to 3. So if we go take this strategy, and the sequence of being discovered for all the vertices is from 1 to 2, 4, 5, and then back to 3. Okay, so that is a DFS. And as a very simple demo comparison here, if we choose to go as broad as possible, like BFS algorithm indicates, if we start from 1, then we will make sure that all the vertices, all the adjacent vertices of 1 are all discovered before we go one more step deeper. Okay, so we will first look at all the adjacent vertices of one that are one distance away, that are one edge away. Okay, so we will discover 2 and 3, right? So after 2 and 3 are discovered, then the current distance is all totally covered. So we'll increase the distance from 1 to 2. For example, we start from 2, and then we will also make sure that all the adjacent vertices that are one distance, one edge away from the vertex 2 are discovered. Like 4 and 5, they are discovered. Okay, so as you can see, the resulting trees are very different from these two algorithms. So the resulting DFS tree is very kind of long, right? Because from the root node 1 to the bottom level leaf node 5, there's 1, 2, 3, 3 edges, right? But for the BFS tree, it's much broader. It's much has a larger breadth, right? It's very broad. So the edges, so the trees is a bit more bushy, and the total depth is not as deep as the DFS tree. As you can see, the resulting the results are quite different. So let's see how DFS can be implemented. So there are two ways, as I said before. There's one recursive implementation and one iterative implementation. Let's look at the recursive DFS. And that's it, just 4 lines of code, okay? And it's quite simple. It takes the graph G, right? Remember the way we represent a graph, right? The G indicates all the vertices and the edges. So, and assume that we use the adjacent lists as the way to represent the graph. The other way is adjacent matrix, okay? But with the adjacency list, it's easier to write the pseudocode like this way, okay? Anyway, and another input is the source vertex, which is similar to BFS. We always need to select a starting point. So the first line of code is to mark the source as visited to be true. So we assume that each vertex has a Boolean property, has a Boolean attributes, okay? And they are all initialized to false. That's our assumption, okay? Then what the DFS does is to simply iterate over all the possible adjacent vertices of the source, right? Because the adjacent vertices for the source is stored in this list, G dot adjacent with brackets, square brackets S, okay? So remember the G dot ADJ, which is short for adjacents, is actually an array, right? But it is an array of lists. So each element in the array is itself a list, okay? So we can use the for loop called upon the one element in the adjacency lists, okay? So for any adjacent vertex of the source vertex S, we will check whether that vertex is visited or not. If it is not discovered, if it is not visited before, then we will call the function recursively, call the function itself recursively on that adjacent vertex. And that's it, as simple as the code indicates, okay? So I think it's easier to understand why this recursive algorithm works by looking at an example, okay? So the given example like this with vertex u, v, w, x, y, we can try run the DFS recursive on the source vertex u, okay? And let's see what the algorithm will return. All right, so assume that any unvisited vertices are painted white here. now, because our first step is to paint the source to be the visited attribute to be true for the source, so we assume that it becomes gray. Okay, and remember the for loop. We will iterate over all the adjacency lists in all of the source vertex, which is V and W, right? And actually, the order is we randomly decide the order. We decide to iterate over V first, okay? But that doesn't matter. You can also decide you can visit W first, but the resulting tree may be different, but it doesn't influence how we analyze the algorithm here. All right, so let's assume that the V is visited first, because V is the initial value of V dot visited is false. So we will call the DFS recursive algorithm on V recursively. All right, so this is the first recursive call. Then in this recursive call, we will and another recursive call is simply the DFS recursive on W, right? Because V and W, they are the adjacent vertex of the source. So within the first recursive call, we will paint the V to be gray, which means we set the visited attribute to be true. Okay, so as the color indicates, V becomes gray first. Okay, and as the algorithm the code defines, we need to, because we are under this recursive call now, we need to go through all the adjacent vertices for V, right? So the adjacent vertices of V include X and Y, right? Because only X and Y go out from V, right? So there will be two new recursive calls here. Let me use another color. DFS recursive on X and the DFS recursive on Y, right? So they are in an even lower level of recursion. And we'll do the same thing, in which we will paint X to be true, right? And now, here's the interesting part. So the X dot visited is, after the X dot visited is changed to be true, according to the algorithm, we need to visit the adjacent vertices of X, right? So that means we need to call DFS recursive on Y. So this call is even at a lower level of the recursion, right? So in this call, painted in pink color here, we will paint the Y to be gray. We'll visit Y here. And after this is done, because Y doesn't have any adjacent vertex, we will return this recursive call, right? This recursive call will return to an upper level, right? After this call is returned, the next will be executed, right? But since this one, within the pink call, V is already set to be visited. So in the next DFS recursive call, this will not be executed, right? Because the vertex Y is already visited, right? Remember, we only will execute the recursive call when the vertex is the visited attribute is false. Okay, but since in the pink call, we change the visited Y to be the Y of the visited attribute of Y to be true. So this planned recursive call will not actually execute it. So we will cross this out. Okay, and then we will go to the top one more recursion level up, and we will go to the recursive call on W. Okay, which will paint W gray. So then at this step, we are done with all the vertices in the graph. Okay. So the resulting tree, if you draw it, you can see that it's U at the top, and then on the right it's V, right? And on lower than V is X, and X connect to Y, and the other branch of U is W, something like this, right? All right, so that's the recursive implementation for DFS. And now let's look at a iterative DFS. And usually speaking, an iterative algorithm takes longer to write, and also it relies on some external data structure. So remember the BFS, we relied on the data structure Q, right? It's a first in, first out algorithm. And in DFS, we rely on another data structure called stack. So a stack is a first in, last out data structure. That means the elements we first put into will be popped out as the last elements. So given this data structure, let's do a little review. The stack here is initialized, and a stack should support push operation. So this push will add an element to the stack, okay? And also it should support pop, okay, which will remove the top elements. So in this example here, 1 is first pushed in, and the 2 is pushing after 1 is inside. So if we pop at this step, then the 2 will be popped out, but the 1 will remain in the dash. So that's the so-called first in, last out. So if we look at the code, we basically define a stack and push the source in, and then we will enter a while loop. So this while loop will not execute, will not exit until the stack is empty. And within each iteration of the while loop, it will pop one element, that is one vertex in the graph, out, okay? And then check whether that vertex is visited or not. If it is not visited, we will visit that. We'll set the visited to be true. And then the interesting part is here, if it is not visited, we will paint it gray, which means we will set the visited to be true. And then we will push all the adjacent vertices of that vertex into the stack, okay? So let's see what the results will be like using a simple example again, okay? So I paste the code on the right, and again, let's use this very simple example. And again, we use the vertex U as the starting point, as the source vertex. So U is first pushed into the stack, which was initialized to an empty stack. Okay. Now we go to the while loop, and the while loop will pop one vertex out, which is U. Okay. And since U is not visited, we will set the visited to be true. So after this is done, the U becomes gray. Okay. And then we will look at all the adjacent vertices of U and push them to the stack. Okay, so U has two adjacent vertices, which is V and W. Okay, so that means we will push V in and push W in. Okay, so this order matters, right? We randomly select that. We randomly choose to push in V first. And you can always select, you can also select to push W first, but that will result in a different order of pop, right? If you push V in and W, and then W following V, then the W will be the next one being popped out, okay? Decided by the nature of a stack. Okay, so V is pushed in and W is pushed in. So that here's the current status of the stack. All right, now let's enter the next iteration, right? We will run pop, and the W will be the element being popped out. And since W is not visited, we will paint it to gray, right? So W is painted here. And we will look at which adjacent vertices W has, right? W is connected to X. So X is the only adjacent vertex of W. That means we will push X into the stack, okay? And V is still in the bottom of the stack. Remember, we first push in V, but now V is not reachable because, again, we will push X into the stack. So in the next iteration, when we run pop, it is not V that get pop out, but it's X. It's the most recently stacked in elements that popped out. So X will be popped out and X will be painted to gray. And then we will look at the adjacent vertices of X, which is V and W. Okay, let's assume. So now here's the interesting part. Although V is already in the stack, that doesn't prevent us from pushing V again, because stack is just another data structure. We can push in the same elements again, just like copy the elements again into the stack. So we push in V for the second time, and then push in Y. Okay. Then we'll go to the next iteration, which is to pop one element out, and Y will be the elements get popped out. So Y is white, so we will paint it gray. And let's look at if there are any adjacent vertex for Y. And luckily, we don't have any. So Y has no adjacent vertex. So nothing is pushed in. So we'll keep pop out the gray from the stack. So V will get popped out and we'll paint it gray. And remember, there's still another V in it. So we'll let the while loop to run and V get popped out. Okay, so before that, after V is visited, we still need to push in X and Y into it according to the algorithm, right? Even though X, Y, they are already visited. So X and Y are pushing back to the stack, but at this step, we already know that all the vertices are already visited. So the algorithm will terminate very soon. So the next, we just need to pop out the Y. And since it's all visited, we will go to the next iteration, pop out X, and then pop out V. And then we have an empty stack. That's the point where we stop. So look at the tree. What do we have now? It is something like U, right? W, X, and V and Y, right? So we can notice that it's different from the previous DFS tree, right? From the recursive implementation of DFS algorithm, it's like 3 on the right, 1 on the left. But here it's more like a Y shape, right? So it's different results. Basically, it's because we use different implementations. The algorithm, the iterative algorithm relies on the stack, and that will basically lead to different orders of when we visit each node. All right. So that's the iterative implementation. So now let's look at how do we modify these iterative or recursive algorithms so that they can record the parent relationship between vertices. And this is quite straightforward. We can just add one line of code, right? We just, when we visit an adjacent vertex here, we will set the pi, which means parents, attributes of the current vertex to be the source where we start. Okay, so that's the simple iteration modification to the recursive implementation. And that means will result in a DFS tree like this, where we can simply record a tree like this. And for the iterative algorithm, we can do the same thing, right? We can result in a different tree like this. I didn't show the code here, but it's easy to identify to add one line of code to record the parent relationship. All right. So let's look at another special issue we didn't cover in the DFS. So it is when you start from some source vertex, but after you have run one round of DFS, you may find that, okay, there are some vertices that's left behind, that's not reachable from the source. That is possible, right? We didn't say that all the vertices are reachable from the source. So this can also happen when you run BFS, breadth first. That's also possible. And so now let's look at this case. If we want to make sure that all the vertices are visited, so we can basically run the DFS for multiple times. Like we can use a for loop to go through all the vertices in the set. So G.V includes all the vertices. So we will simply check whether the current vertex is visited or not. If not, then we will call the either the recursive DFS or the iterative DFS. So these two will make sure that all the vertices are visited. So this also apply to BFS, okay? Because the previous BFS algorithm, we didn't say that we must have all the vertices reachable. So if we want to make sure that all the vertices are at least visited, then we can add a for loop here. Okay, so the results of such a for loop based DFS, a very thorough examination of all the vertices will basically result in a forest. Okay, so for example, if there's some unreachable vertices from the source, then DFS will generate multiple trees, not just one tree, but multiple trees which basically form a so-called forest. So for example, if we run the DFS, if in the DFS call, we have the DFS on W is first called. So that means we start from W, all right? So it's easy to check that this call of DFS recursive will first find the vertex X here, right? And X, from X we'll go to V, maybe Y and V, right? So after these four vertices are visited, since the U is not reachable, right? There's no edges from X to U or from V to U. So there's only one directional connection from U that leaves U to other nodes, to other vertices. So the U will basically in an isolated structure. Let me use another color. So the U will be an isolated vertex which its own forms a tree. Okay, although it just has one node, right? So in other more complex cases, then U can have other connections like that, right? If we start from U, then that will result in a different tree, which is not connected to the first tree. So that's why we say this is a forest which contains two trees. All right. So we introduced the DFS forest, and now let's look at, as I said before, we need an enhanced version and a more advanced version of DFS, so that DFS will be more useful in the next several algorithms that we're going to cover. Okay, so in this enhanced version of DFS, we will basically, what we'll basically do is we need to color the vertices during the search, okay? And we also follow the rules that all the vertices are initially white, and after that, after it is first discovered, it becomes gray, and after it is finished, it becomes black, right? That is when when all the adjacent list has been completely examined for one vertex, then we'll color it black. So it's similar to the white, gray, black notation in BFS. Okay, so that's one principle. That's one rule we need to follow. So another more important rule is that we need to record the timestamps for each node, for each vertex. So we use two attributes for each vertex to record two timestamps. The v.d, which is for discovered, it records the timestamp when v is first discovered. Okay, so it is the time where when v becomes great. And the second attribute is v.f, which is for finished. It records the time when v's adjacency list is finished. And that is also the time when v becomes black from gray. So that's two important timestamps, d and f, okay, which is the discover time and the finish time. So we need to record that. So in order to have, so first of all, we must have the values of d must be smaller than f, right? Because a vertex must be discovered first before it is finished. So that is always true. And a relationship between the color is that, between the D, F, and the color is that, so a vertex U is white before the timestamp U.D, and it is gray between D and F, and it remains black after the timestamp F. So we'll see that that's a very obvious fact later. So an important technique is that we need to use a global variable, which is called time. Okay, so this time is globally accessible in the whole procedure because we will use that time to record the global timestamp for all the vertices. Okay. Now let's look at the procedure. Okay, so it's called DFS, and inside DFS, we notice that there's a DFS visit. So this is actually a helper function, and the technical part is actually within this DFS visits. And the function of DFS is to do the initialization. The line 1 to 4 is to go through all the vertices and paint them white and set the parents attribute to be none and initialize the global variable time to be 0. All right, and then we will start visit all the vertices going through a for loop, right? Go through all the vertices, and if the color is white, we will call the DFS on that vertex. Okay, so the DFS visit is where the actual DFS algorithm is defined. So let's look at the DFS visit. All right, so this DFS visit as now let's go through the lines slowly, okay? So first, it increments the time stamp by 1. That is because we are going into that vertex. That will cost us some time, right? We will need to record the timestamp. And after we increment timestamp by 1, we will assign that new timestamp to the D. So it actually indicates the discover time for that node. So for the source node, because all the vertices are initialized to 0, right? So the time is initialized to 0. So for the source vertex, it will have the timestamp 1, right? Because we'll need to increment from 0 to 1. And then we will paint the color to be gray because it is the first time that this vertex is visited, okay? And for each adjacent vertex of U, which we indicate by V, we will also check whether it is visited or not, right? If it is white, which means it is not visited yet, it is not discovered yet, we will set the parents of V to be U, right? Because V is reachable from U and V is not discovered yet. So we will set the parent relationship. And then we'll call the DFS visits recursively on that vertex. So this step is quite similar to the DFS recursive implementation, right? The only fancier place is where we record the timestamp, right? And record the parent relationship. Okay, so after all the adjacent vertices of U is visited, after this for loop, what we need to do is to paint the color of U to black, right? This is because all the adjacent vertices are visited now. There's no white and there's no gray adjacencies list. We need to, there's no white adjacent lists, adjacent vertices. So we need to paint U to be black. And also we will increment time again by showing that this is the time where when we finish the current vertex U. Okay, by finish we mean we have completely examined all the adjacent list. Okay, so there are two line of code where the time, global time is incremented, and we will see the effect, an interesting effect of this running these DFS visits on the graph. All right, let's look at this example. We have 6 vertices and several edges. It's actually 8 edges, right? And there's one special edge that points towards itself, which is okay. We can allow for these edges. So we assume that the DFS visits will start on the source U. Okay. So since the time is initialized to 0 and it will increment by 1, so the time, the discover time is 1 for the source. Okay, so we'll use the number on the left of the slash to be the discover time, and the right half to be this place will record. We'll write the U dot F here. Okay, so on the right is U dot D. Okay, we'll write in this style. Okay, so on the right it's the finish time. So after this step, U is discovered. It's painted to gray, right? Then we will go through all the adjacent vertices of U, which gives us V and X, right? So we assume that we go to V. And of course, we can choose to go X, but the results it's the same procedure we need to go through. So assume we go to V first, and remember that we need to increment the time stamp, right? Indicated by this line of code. So the discover time for V is 2, right? That means it is the second vertex being discovered. Okay. And we'll look at the adjacent vertices of V, which includes Y, right? So we'll call DFS visits on Y, which will increment the time again and assign that time global timestamp to the D attribute of Y. So the Y will be the third discovered elements. Okay, and then we'll look at adjacent vertices of Y, which includes X. Okay, so X will be the fourth, right? And then we're starting from X, we are going to look at the adjacent vertices of X, which includes V, right? Which only includes V. But since the color of V at this point is gray, so it is not white. So the if condition is not satisfied. So we are not going to set we're not going to let X to be the parent of V. Okay, so there will not be a highlighted edge over here. So again, please pay attention to the highlighted edges here. Those edges means that there is a parent relationship between the two vertices. Okay, and there will not be a parent relationship between x and v, because by the time we start from x, we find v to be its adjacent vertex, but v is already visited, so we shouldn't run the code here. Okay, and we need to, at this step, because the x, all the adjacency vertices of x are visited, we are actually reaching the line of code here. We need to paint the color of x to be black, right? And also there's a technical term here, which I'm not going to cover here, but we'll later see. The edge points from x to v can be labeled as a back edge because it points from some descendants to some ancestor, okay, which we will cover after we are done with the whole process, okay? And we just need to know that next step is that we need to color the x to be a black vertices. Okay, so x will be colored to be black and the time will increment by 1. So the f of x will be 5, right? Then after x is visited, after x is done, then we will trace back to the upper level, to the previous level, which is y, right? When all the adjacent vertices of y is visited, we need to increment the timestamp by 1 and set the finish time of y. So this time for y, it needs to be 6, right? And after y is done, we also increment timestamp from 6 to 7 and assign the finish time of v to be 7. And lastly, until we reach the point u, right? And also, again, here we labeled a new edge from u to x to be the forward label, which we're going to talk about later, okay? And more importantly, we need to finish, set the finish time for u to be 8, okay? So all these numbers on the left are done, okay? And we have one tree available now, which means u has 1/8, which means u is the first vertex being discovered, and it is the 8th. It finished at the timestamp 8, and v is discovered at timestamp 2 and finished at timestamp 7, and so forth for y and x. Okay. So since now there's no output edges from this part to any other vertices in the graph, there's one DFS tree done. Okay, so now we need to consider the right part, right? Assume that we start from W, and remember the global time remains. So from this 8, we will increment it to 9 when we first visit W, okay? And the D property for W is 9, right? And there's a special edge detected, which is cross, which is not important here. Okay, we're gonna talk about it later. So the adjacent vertices of W include Z. So we will visit Z and increment the timestamp to 9, from 9 to 10. And Z itself has another edge that points back to itself. It's also a back edge. And Z has no other adjacent vertices. It will be painted to black, and the finish time is recorded. And then we'll trace back to W. We'll record the finish time for W to be 12. Okay, so we're done with these parts now, and the second DFS tree is built. So now we have 2 DFS trees, which forms a DFS, so-called DFS forest. All right, look at this forest. It looks like this. Oh. right? It looks like this is the whole thing we have. And if we think of it, puts U upon as the root node, it has the dark edges like here. These edges are tree edges. And the second tree is from W to Z, right? These are the two trees. And the dashed lines, B, this edge in middle, and this edge from U to X, we'll talk about it on the next slide. So these are special edges which can be identified through the process of DFS. So we can basically define four types of edges in the DFS forest produced by running the depth-first search. So the first is the tree edges. These are simply the edges in the dark black color here. These are the trees. And these tree edges indicate the parent relationship. So along these trees, U is the parent of V, and V is the parent of Y, Y is the parent of X, and so on. Okay. And for any other edges, the back edges, for example, these back edges from X to V, it connects a vertex to an ancestor in the tree. Okay. And also the self loop also is considered as a back edge. Okay. So whenever you have an edge starts from a vertex pointing back to its ancestor, the ancestor could be a direct parent or the parent of parents, and so on. So it's recognized as back edge. The third type is called forward edge. It's indicated in this case, it is from a vertex to a descendant, to a child node. It could be a direct child. So in the case, if it's a direct child, then it's a tree edge. If it's a descendant, like a child of child, then it is a descendant edge. It is not a tree edge. Okay. And the last type is those between trees. All the other types of edges are the cross edges, like they cross different trees. So this is the interesting results of the running the DFS. And the DFS, these edge types can be identified by examining the colors. So if we are connecting to a white node, white vertex, which is not discovered yet, then we are creating a tree edge. Then if we are connecting to a gray vertex, which means it's already visited, now we are visited it again, which means it's an ancestor. So that will give us a back edge. Okay. And a black, which if we are looking at if the edge is connecting to a black vertex, then it is a cross edge. So these different types of edges will be useful in, like, for example, if we want to determine the dependency relationships between edges. For example, the vertices can indicate an important procedure, an important step in a procedure. Then the back edge means that we need to go back to the previous step, right? And the forward edge means that we need to like skip through some steps. Alrighty, so the last point, let's look at the running time for DFS. All right, so first we have two procedures, right? The first is the DFS, and this DFS is simply initialization. It needs to go through all the vertices, right? So from line 1 to 3 and line 5 to 7, we basically need to go through all the vertices, right? So that'll take us so for line 1 to 3, it'll take us big theta of V times. And for line 5 to 7, we need to consider the time efficiency of these DFS visits, right? So within this DFS visits, it actually calls exactly once for each vertex, because it will only call DFS when this vertex is not visited, right? If it's visited, it will not be called again. So the good news is that DFS is only called once, okay? And within this DFS call, line 4 to line 7 is the critical parts. It is a for loop, right? It basically examines all the adjacency vertices for the node, for the vertex U, right? So it actually runs that many iterations. And we know that for all the vertices in the graph, if we add the length of all the adjacency lists together, that will be at the scale of the total number of edges, right? Because for the vertex that connecting to its adjacency vertices, we are actually counting the number of edges. And if we take into consideration of all the vertices, then that will give us the estimated number of all the edges in the graph. So combining these two parts, we can easily come into the conclusion that the time step for DFS is basically at a scale of V plus E, big zeta of V plus E, which is determined by the number of vertices and the number of edges together. So that is similar to the BFS. And we will find that in the latest lectures, the DFS is more useful in to help us implement more advanced algorithms like topological sorts, and to find the strongly connected components in the graph, which will be a more advanced tricks. So that's it. That's the content for today. It is the DFS. We have two types of implementation: the recursive way, the iterative way, and a advanced an enhanced version of DFS, which we record the starting time and the finishing time. And that's it for the lecture today. And if you have questions, please let me know. I will upload the video later and publish the quiz question. All right, looks like we don't have questions. Thank you for coming.